All right, well, thanks for coming here on a cold night. I'm talking to you tonight from a super secret undisclosed location. Normally I'm at the school, but I have at least a short-term opportunity to do the class from elsewhere that's a little more convenient. So if there's any, I don't anticipate any technical problems, so let me know if there are any, but I think we'll be fine. Let's go over the quiz here, and then we'll dive into chapter 2, which you can see is all about fractions, which is everybody's favorite topic. All right, quiz, which is, again, things we did last time. We want to write some things in what we call standard notation. Right now, that 3 to the second power is in what's called exponential notation. So we want to do this process called square, or second power. We know what it means. It means 3 times 3. 3 times 3 is 9. We have our X square button, which is a special exponent button on the calculator. So it takes something to the second power, right? All right, there we go. Number 2 says, let's take the number 4 and raise it to the third power. We call that cubing that 4. Again, it means 4 times 4 times 4. Now, I don't have a cube button. Maybe you do, but I don't. But what I do have is a generic exponent button, which is that upside down V looking button. 4 to the power of 3 gives me 64. Okay, number 3 says 5 to the power of 4. Again, that means 5 times 5 times 5 times 5. 5 power 4, 625. All right, now maybe we knew all those or could easily figure them out. Now number 4 is no different, other than it's just not one we have committed to memory, probably for sure. And the process to figure this one out maybe is a little harder, because it would be 2.36 times 2.36, and that's not very fun to figure out. Not that we can't, but if we square it in the old calculator here, we're going to get 5.5696. Okay. Number 5, 10 to the power of 6. Okay, we've talked about, we're going to talk more about these powers of 10 and what they're all about. Well, 10 to the power of 6 just means I've got a 1 with 6 zeros after it. Okay, we didn't really have to go to the calculator, not that we couldn't have. 10 to the power of 6 is going to be a 1 with 6 zeros after it. Okay. And finally, number 6 now. 10 to the power of 0. Whenever I have a number raised to the power of 0, what do I get? 10 to the power of 0, I'm going to get a 1. Okay, so anything to the power of 0, with the exception of 0 itself. If I try to do 0 to the power of 0, I'm going to get an error message here. Let's try it. Okay, no good. But anything else to the power of 0 is going to give me a 1. Okay, so that's going from exponential to standard. If we want to go the other way around, number 7 says take that 1,000 and turn it into exponential notation. Well, now we're just moving the decimal. We're saying, well, what would that be? It would be, there's 3 powers of 10 there. Well, that's going to be 10 to the third power. Okay, number 8, I've got 10 million. I count the zeros. I've got 1, 2, 3, 4, 5, 6, 7 zeros there. So that's 10 to the 7th power. Okay, number 9 has got just 10. And you say, how do you write 10 in exponential form? Well, that's going to be 10 to the power of 1. Right, and then finally 10. What do I have here? 1, 2, 3, 4, 5, 6, 7, 8, 9. I've got 10 zeros after that 1, right? So that's going to be 10 to the power of 10. Okay, everybody happy with those?
Yes, sir.
Right.
Yes.
The process of taking a root is like the reverse process of taking an exponent. Okay, and the most common root is what we call the square root. It's got a symbol like that. We put a number underneath the square root sign, and we're saying, go do the reverse process of squaring. Okay, we have a square root button on our calculator. Mine is above the x squared. It's kind of in the margin there, if you will. It's in between. I have to hit a shift button to get to it. Come on, focus. Now everybody knows where your x square button is, or your square root button is, right? So square root of 9 is going to be a 3, right? Because 3 squared is 9. Fair enough. Number 12 says the square root of 27. Okay, now my calculator is going to give me a decimal. Now we had, I think, an example. Oops, I got to say square root. We had, I think somebody had their calculator set to just reduce that, put what's called reduced radical form. So I'm going to get 5.196, blah, blah, blah. Somebody might get, what are we going to get? You might get 3 times the square root of 3. Anybody get that?
Yeah, I did.
Okay. Your calculator is just set up to what's called simplify that square root as opposed to turn it into a decimal. It would be a simple correction to get it out of that mode. It's some kind of mode issue. So if you look into it a little better, I can help you if I know what calculator you have. We can get that out of there so it gives you the decimal. But that's all that is. Now, if you take this and you say 3 times the square root of 3, which is what that is, now I would think even your calculator would give us the answer. 3 times, I mean, mine will because it's already set up. But if you do that on your calculator, 3 times the square root of 3, you should get the decimal then, I would think. Okay, what do I have? I got an extra number 12 there, I guess. So, well, we'll do number 12, another number 12. Here it says the cubed root of 9. Okay, well, now we're not doing square roots, we're doing cube roots. And my calculator, above the x square, above the exponent button, the upside down V above there is my generic root button. So what I would need to do is put my 3 in first to say, hey, we're taking a cube root here. Then I hit my root button, and then I put my 9 in there, and then I hit my equals. And again, cube root of 9 is not a nice pretty number. It's going to give me some decimal. I'll call it 2.1. Okay, number 13 is a cube root of 27. That will be a nice number. Okay, so I'm going to say 3 for cube root. I'm going to hit my generic root button. I'm going to put that 27 in there, and I get a 3. All right.
So whatever number is in that little check, if it was like a 4, you would say that was like 27 to the power of 4.
Be the 4th root of 27. Yeah,
okay.
To that we would say 4, and then our exponent button, and then 27, and 2.2, blah, blah, blah.
Perfect. Thank you.
Sure. All right, the next handful are all about multiplying powers of 10. Again, pretty straightforward. I want to take 5 times 10 to the power of 3. That just means I got a 5 with 3 zeros after it. You don't really need to use the calculator. You can, but you don't really need to. 10 to the 3rd is 1,000. 5 times 1,000, 5,000. 15, 47 times 10 to the power of 5. Well, that's just going to be 5 zeros after that 47. Go back and figure out what that number is, 4,700,000. Okay, now 16 is not quite as, you don't just tack zeros on the end because I've got this decimal here, it's 2.36. So 2 of these powers of 10 are just going to shift that decimal to make it 236, but then I'm going to have 2 more powers of 10. So on top of my 236, I need a couple of zeros. So it's 23,600. All right, and then 17 is similar to, or excuse me, 5.4391 times 10 to the 2nd power. Well, I'm only going to move that decimal 2 places. So it's going to be 543.91. All right. Order of operations, number 18. 6 squared plus 4 times 3 minus 1. Parentheses, exponents. Multiply and divide go together. Add and subtract go together. Well, there are no parentheses, so I'll knock out the exponent here. 36 plus 4 times 3 minus 1. Now I'll multiply 36 plus 12 minus 1. And now I'll add and then I'll subtract, right? So it's 48 minus 1, 47. Everybody okay with that one?
Yep.
Sweet. Alrighty, let's see what's cooking here. Number 19, I've got 2 parentheses 5 minus 1 plus 4 squared times 3. Again, parentheses first. So oops, I didn't do anything. Parentheses first, 5 minus 1 is 4. Okay, we really could knock out the 4 squared in that same maneuver. We kind of talked about that a little bit last time. The reason we could is this plus sign protects it from the 2 times 4. So I really could have knocked it out on the next step, but okay, I won't. Now I will. 16 times 3. Okay, you see I have a multiplication, an addition, and then another multiplication. So this addition really separates these two things. There's no reason I can't knock them out on the same shot here. So 2 times 4 is 8, plus 16 times 3, 48. Then I take 8 plus 48, 56. All right, everybody cool with that one?
Yeah.
Yeah.
I like it. All right, 20. 2 radical 25 minus 3 squared in parentheses, now minus 1, plus 4. Okay, parentheses first, right? So inside the parentheses, you've got your own little order of operations to worry about. Okay, well, what's going on inside the parentheses? Maybe we could at least do this together. 3 squared is 9, and then minus 1 will be 8, right? We could knock that out in one shot. Okay, so I've done everything inside the parentheses in proper order. I'm going to move now beyond the parentheses to exponents, and that includes roots. So that's 2 radical 25. Well, radical 25 is 5, and 2 next to a radical means times. So 2 times 5, okay? The parentheses at this point serve no purpose, so I'm not going to write them again. I'm just going to say minus 8 plus 4. Okay, so I have a multiplication, a subtraction, and an addition. I'll do the multiplication first. Okay, and then remember, addition and subtraction is the same level of priority. Whichever one you hit first, you do first. So I'm going to subtract first here and get a 2 plus 4, 6. All right, 21. Big old fraction, which is good because tonight we're going to start fractions. Let's see here. All right, I've got this. So I really have 2 separate problems, a top and a bottom. I'm going to follow the rules on each one, and at the very end, I'll worry about the fact it's a fraction. So what's going on up top? I got parentheses, I got exponents, I got subtraction. I'll knock out the parentheses up top. 3 plus 1 is 4. Again, I really didn't need to put that parentheses around the 4. It didn't kill me, but I didn't have to do it either. All right, down here in the parentheses, we have 2 things. Let's knock them both out. We have 4 squared is 16, but then minus 1 will be 15. Okay, times 2. Up top, 5 squared is 25, and then again, I had minus 4. And then 15 times 2 is 30. 25 minus 4 is 21. So I'm left with 21 over 30. And this is where we haven't really talked about how to reduce this fraction. That's something we'll get to. So I guess for tonight, we would call this a finished answer. But after we talk about reducing a fraction, I would want us to go one more step with this problem. But for now, I guess we'll call that good enough. All right. All right, then we had a little bit of geometry we talked about. We have parallelograms, rectangles, and squares, perimeters, excuse me, perimeters and areas. So I had some formulas on the next page and also volume of a box, essentially, a rectangular prism, we call it. Think of it as a box. 22 wants to know the perimeter and area of a parallelogram here. So what does that mean? The opposite sides are parallel. We give them little names. We call that side the base. The bottom, the base, we call the side, and then the height, h. Okay, well, perimeter said we have twice times the base plus twice times the side. Perimeter just means you walk around the outside. How far did you walk? Well, I got a B, a S, a B, and an S, and that's a lot of BS. Okay, 2 B's and 2 S's. So what do we have here? On this example, we've got 9 feet, and we've got 6 feet for my B and my S. So my perimeter is 9 feet times 2. I should have wrote the 2 first, but it doesn't matter, right? Community property says no problem. I can write the 9 and then the 2. And then 2 times 6. So my perimeter is going to be 18 feet plus 12 feet is going to be what? 30 feet. Okay, everybody okay with perimeter? Distance around. Area says how much surface do you cover, right? How if I had to get a paintbrush out and paint, how much surface am I talking about here? Well, area is now base times the height for a parallelogram. So I don't need to know the side length, but I do need to know the height. And the height for this problem was 5 feet. Okay, so area is going to be 9 feet times 5 feet, okay, which is 45, but then feet times feet is square feet or feet squared. All right. (23) is a rectangle, which is just kind of a simplified parallelogram. You notice these formulas are all really similar because these shapes are really similar. A rectangle, we just think of a length and a width because the width is the same thing as the height. The parallelogram is kind of like a squished rectangle. So now we just got a regular rectangle. Perimeter is twice the length plus twice the width, okay? So 2 times 12 meters plus 2 times 5 meters. So 24 meters plus 10 meters. So the perimeter is going to be 34 meters. Okay. Area of a rectangle is length times width. So what's that going to be? 12 meters times 5 meters. 12 times 5 is 60. Meters times meters is meters squared. Okay. A square is now just a special rectangle. It's even easier because all the sides are the same. Okay, it's just like having a length and a width, but they're both the same. So we give it a new name. We call it S. The perimeter would be, walk around, you got 4 S's, right? So 4 times S is my perimeter. In our little example here, S was 7 inches. Each side is the same at 7 inches. So 4 times 7 inches. So the perimeter is 28 inches. Area of a square, it's that same length times width, except in this case, the length and the width are both S, so it's S times S, but we can more conveniently call that S squared. So that's 7 inches squared. 7 times 7 is 49. Inch times inch is square inch. All right, and finally, volume of a rectangular prism or a 3-dimensional box. Okay. How much stuff can I put inside the box? Well, I need to know 3 dimensions. Okay, a length, a width, and a height. Doesn't matter which is which, right? I mean, if I turn the box this way, you know, the length, the width, and the height, it's all relative, right? Which one you want to call which? It really doesn't matter because I'm just multiplying 3 things together and the order does not matter when I'm multiplying. So it doesn't really matter what I call what here, okay? So I'm going to take the 5 feet times the 12 feet times the 4 feet, okay? And let's just, that's 240, right? But let's see, 5 times 12 times 4 is going to be 240, but this time I have feet times feet times feet, so it's going to be cubic feet. Okay, how was that? Everybody okay with all those problems?
Yes.
Yeah.
All right, so we had our, our first homework was that was part of it. That's still stuff we talked about last time. So we're all good to go with that stuff. We're going to move on now to new stuff here tonight. And we're going to dive into chapter 2. So I've got it up on the screen, and if you have your own book, of course, feel free to follow along. It's all about fractions here tonight and really part of next week, okay? Everybody's favorite topic, I know. I always remind you that math is fun. And when appropriate, I remind you that fractions rule. And sometimes I sneak a baby in there, right? Tonight, that definitely applies, okay? Fractions rule. So let's talk about it. What are we gonna do? First of all, the beginning of each chapter has kind of the little cute or otherwise tragic story, depending on the circumstance. This one is a tragic one, when fractions kill. I'm not going to read it, but if you take the time, it was some guy, I think, over in England. He bought some caffeine powder and was going to load up on caffeine to go out and party all night. Well, I think the instructions said he's only supposed to take 1/16 of a teaspoon, and he took 2 teaspoons, 2 full teaspoons. So like 32 times as much as he was supposed to. And I think the guy died as a result. So pretty dangerous when you misjudge, a dosage on something. So fractions are part of that world. So let's talk about them. Okay, we've all dealt with them before to some degree. Maybe we've avoided them to some degree, but we've certainly all dealt with them. Kind of the anatomy of a fraction. You have this number on top, which we call the numerator. Then we got the fraction bar. And then we've got the denominator. Okay, how hard could that be? Numerator, fraction bar, denominator, that's it. Okay, so the numerator and the denominator are numbers, of course, okay? And it's representing a part of a whole. You can think of it as part of a whole. Okay, but it could be more than the whole. So, that when you think part of something, you think less than the whole, but it doesn't have to be less than the whole. So, that's kind of take that definition with a little bit of grain of salt. They're part of something. It could be more than the whole. All right. When we have, these two numbers and we have the smaller number on top and the larger number on the bottom, well, think about it. Well, first of all, a fraction is a division problem, right? Let me say that. Okay. That's no different than me saying, numerator divided by denominator. I'm going to just scribble it because I can't write it out. Okay, division problem. Numerator divided by denominator. That's all a fraction is. So if I take a smaller number divided by a larger number, I'm always going to get something less than 1. Okay, and when that happens, we call it a proper fraction. Okay, and that's when I say part of a whole, that's what I mean. Not the whole thing, something smaller than 1. 1 would be the whole thing, something smaller than the 1. Okay, if the same numbers match, a match top and bottom, then I'm going to get exactly 1 because something divided by its exact match is 1. And if it's the other way around, larger on top and smaller on the bottom, that's going to divide into a number greater than 1, and we call that an improper fraction. All right, so far so good. Generally speaking, we frown on those impropers, okay, and we convert them to something called a mixed number. We'll get to that shortly. Okay. Part of a whole, part of a whole, part of a whole. What does that mean? Well, let's think of the old pie chart here. Right, a pie. I've got a 4-piece pie, right? So if I have a 4-piece pie and I want to discuss something about these pieces, it's all going to be relative to how many pieces there are. So that's my denominator. It's a 4-piece pie. Okay, and if I'm interested in one of those pieces, then I would say the fraction I'm interested in is 1 out of 4. And it's a nice visual. You can see 1 piece is shaded out of 4 total pieces. Okay. What if I'm interested in 3 out of those 4? Well, that means it's a 4-piece pie and I'm interested in 3 of those. So that would be the visual for 3 out of 4. All right, I'm going to try really hard here in math class to always write my fractions like I said, numerator, fraction bar, denominator. Okay, some people write their fractions like this. Okay, and in my other life, I do that. I try not to do it in math class because it's not quite as easy to see that, hey, I've got a top and a bottom here. Okay, now you could even write it like this with no top and bottom. It's still the same thing. All three of those things are the same. And of course, so is this. Okay, but when we're talking fractions, I really want to see that top and bottom. I'm going to write it like that. So if I slip up and do this, for example, I'll try to catch myself. Okay, but I really want to show it like that. All right, fair enough. So I got a 1 out of 4 pieces. I've got a 3 out of 4 pieces. Those are both what we would call proper, because 1 divided by 4, that's something less than 1. 3 divided by 4, that's something less than 1. Okay. What if I have 4 out of 4 pieces? Well, you say you got the whole pie then, buddy, right? You got all 4 pieces. 4 divided by 4 is, of course, 1. So that would be 1 whole, pie in this case. So if I have the fraction of numerator and denominator the same, then it would be just a whole, 1 whole. It's not a part. What if I have this now? What if I have 2 pies? Okay, and I've got this whole pie working for me, and I got an extra piece over here. Well, when we have this situation, we're still thinking of it as a 4-piece pie, okay? So my denominator is still 4, but I've got 1, 2, 3, 4. I've got 5 pieces. Okay, so you can see I've got more than 1 whole piece, okay? And if you think about it, well, it would be 1 whole and then 1 out of 4 more. So we would say 1 and 1/4, and that's what we call a mixed number. And we'll talk about how to convert. These two things are equal. They look a little different, but they're the same. We'll talk about how to convert between the two. All right, so far so good. Now the book didn't use my little pie chart. It used this rectangular shaded boxes, but I think the pie chart's more fun. And math is fun, so I do it that way. Wouldn't you agree? Uh-oh, tough crowd.
Of course, of course.
All right, I mean, worried there for a minute. All right, so our next page kind of talks about the old numerator and denominators that I've kind of mentioned, the fraction bar, sometimes referred to as a slash. All right. All right, a couple things we're going to do with these fractions. Well, we're eventually going to add and subtract them, but we're going to always want to do something called reduce them to lowest term. So in order to do these processes of adding, subtracting, and reducing, we need to learn a couple other properties of numbers, really, and one of which is called finding the multiple of a number. Okay, the multiple of a number. This starts on page 62 here. All a multiple of a number is you take that number and you multiply it by what we call a natural number. The natural numbers are just the counting numbers. You start at 1, 2, 3, 4, and off you go. Okay, so that seems like no brainer, right? So multiples of 4, 4 times 1 is 4. 4 times 2 is 8. 4 times 3 is 12, right? 4 times 4 is 16. These are what we call multiples of 4, okay? You could just keep going, right? 20, 24, 28. So in other words, count by 4, right? It's another way to think of a multiple. You can think of it as, hey, 4 times 1, 4 times 2, or you can just say count by 4, count by 5s. 5, 10, 15, 20, 25, 30, 35, etc. Okay, so finding the multiples of numbers is pretty straightforward. That the mechanics of finding it. Now, why we might want to find it, we'll talk about it shortly. But how to do it is just that. You're either think of it as counting by that number, or you're just going to take that number and multiply it by 1, 2, 3, 4, blah blah blah. Okay, so example 2 just asks us to do that here a couple times. Show that 2, 4, 6, 8, and 10 are all multiples of 2 by writing it out. So 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6. 2 times 4 is 8. Okay. 2 times 5 is 10. So we have demonstrated that 2, 4, 6, 8, and 10 are all multiples of 2. Okay. Example 3, same idea. Find the first 5 multiples of 16. Well, maybe we'll do this one the other way. Just count by 16. 16, 32. 48, 64, and then 80, right? same thing. How did I get that? Well, that was 16 times 1. That was 16 times 2. 16 times 3. Okay, that's what the multiples are all about. All right, so we're going to eventually need to do this. We're going to need to take numbers and find multiples of those numbers, and then we're going to be looking for matches. You know, we're going to do it for more than one number at a time. Like up here, I did it with the 4 and the 5, and we're going to want to inspect our multiples and say, aha, check this out. There's a match here, 20 here and 20 there. What do you know? Okay, we're going to be looking for what we call the least common multiple, or the smallest match between those numbers. Okay, so we'll get to that in a little bit. All right, so another thing we're going to want to do is we're going to want to be able to take a number and look at it and say, can I divide that number by 2, or can I divide it by 3, or by 4, or by 5, and get a nice pretty whole number out of the deal? I don't want some decimal. I want to divide and have a nice pretty answer. Okay, so that's a question that's we need to ask ourselves. Now, it's called divisibility at the very bottom of page 62 here. Now there's a cute, clever, you pick your adjective here. There's a little procedure on how you might do it. Okay, now there's a lot of steps there. There's 9 steps to remember for this procedure. If it were just you and me, you know, with our best buddy, the calculator here, you can test these 9 steps really quickly. Okay, we'll run through it by hand, and then we'll also just kind of use the calculator and see. But if we're in a pinch and we really need to figure out whether or not something's going to divide easily, these are some rules, if you will, or conditions that have to apply, or it's not going to be divisible. So if I want to know whether or not I can divide something by 2, okay, that one's pretty easy. If it's an even number, so if it ends in a 0, a 2, a 4, a 6, or an 8, I can cut it in half, right? Anytime I have an even number, I can cut it in half, which means divide by 2. So 2 is pretty easy to understand whether or not I can divide something by 2. If it's an even number, I can. Odd number, I can't. And get a whole number, right? I mean, of course, you can always divide by 2, but you know, 535, if I try to divide by 2, it's not going to be a whole number. Okay. 536 is even. It will be a whole number. Okay, so that's what we're looking for. Can I divide it and get a whole number out of the deal? That's the question. Well, what if I want to divide something by 3? Okay, the second step there. Well, it'll divide by 3 if the sum of the digits is divisible by 3. Now, what does that word sum mean again? We got to review a little vocabulary here. What does sum mean?
Add.
Pardon me?
Add.
Add, right? Sum means add. Okay, so the sum of the digits. So if I've got 8,341, and I want to know, can I divide it by 3 and and get a nice, pretty whole number out of the deal? Now again, I'll just stick it in the old calculator and find out, right? 8,341 divided by 3, it didn't work. Well, if we didn't have the calculator, we didn't want to divide it by hand. Here's what the step says. If the sum of the digits is divisible by 3, so if I take 8 plus 3 plus 4 plus 1, add these up. So 8 plus 3 is 11, 15, that would be 16. If I can take 16 divided by 3 and get a whole number, then this one will also be divisible by 3. So it's, of course, much easier for me to figure out whether or not 16 divided by 3 is going to work. Okay, it doesn't work. The big number didn't work. Okay, if I just made that into a 0 instead of a 1 there, then we would have got 15 over here, right? 15 divided by 3, that works, right? So that means this is going to work. So if I take 8,340 and I divide it by 3, look at that, whole number. Okay, so that's the test for dividing by 3. What about how do you divide by 4? If the last 2 digits form a number that's divisible by 4, okay? So I could take that same 8,340, and what this step says, ignore the 8,300, just grab that 40, and if I can take 40 divided by 4, I'm good to go, okay? Dividing by 5, well, I think that one's pretty obvious. We think we all know that when you divide by 5, it either has to end in a 0 or a 5. You know, because when you count by 5s, 5, 10, 15, 20, you always end in a 0 or a 5. So that's the only way I could divide. Okay, 6, it would have to pass both tests for 2 and 3 in order to be divisible by 6. So it would have to be an even number, and we would have to be able to do the sum of the digits as divisible by 3 in order for 6 to work. Okay, 7 doesn't really have a good test. If you see what it says for 7, if the division has no remainder, well, that counts for all of these. If the division has a remainder, it's not a nice, pretty whole number. Okay, so in other words, 7 doesn't have a good trick. So that's a catch-all. 8, if the last 3 digits form a number divisible by 8. Okay, so we're just going to grab the last 3 digits, 340. Can I divide 340 by 8? Okay, if the answer is yes, then 8,340 divided by 8 will also work. Okay, 9, if the sum of its digits is divisible by 9. So here again, I would want to add the 8, the 3, the 4, and the 0. And if that number can be divided by 9, then 8,340 can be divided by 9. Okay, and finally 10, that one I think is pretty obvious. If it ends in 0, we can divide by 10, otherwise we can't. So let's work, we will work an example following all these little rules, but what I would, if it were just me sitting here, ask the question, does 8,340, what can I divide it by? I would start testing it, well, it's even. I know I can divide by 2. I can divide by 3. We figure that out. I would try to divide by 4. Okay, you just try it. You just try all the possibilities. Okay, what about 7? Will that work? Probably not, right? No. So again, with our best friend, the calculator, we don't really have to go through every agonizing step. But again, it's nice to have this resource available to us. So let's go ahead and try example 4. It's asking us questions here now. We have 874 or 873, and it's saying, hey, which one of these can I divide by the number 4? Can I divide by 2? Well, that one I think is obvious, because if you want to divide by 2, it has to be the even number. So an odd number we can never divide by 2. So it would have to be 874. Okay, we have 275 or 270. And the question again is, which one of these numbers can be divided by 2? Even number. Okay, 2 is easy. 427 or 423. Now, neither one of these is obvious to me, right? The question is, which one can I divide by 3? Well, remember our rule for dividing by 3s. If the sum of the digits can be divided by 3, then the big number can be divided by 3. Well, what's the sum of our digits here? This is 4 plus 2 is 6 plus 7. This is a 13, and this is a 9, right? Well, 13 I can't divide by 3, but 9 I can divide by 3, right? So that means 423 I can divide by 3. Okay. What's our next one here? 5,912 or 5,913. The question is, which one can I divide by 4? Now, the test for dividing by 4 was if the last 2 digits form a number that can be divided by 4. So that means I only need to consider the 12 or the 13. Which one of those can I divide by 4? The 12. All right. 5. We have, 80 or 82? Again, 5 I think is pretty obvious. It has to either end in a 0 or a 5 to be divisible by 5. 56 or 65, also asking the question about divisibility by 5, so it'll be this one. 804 or 802. And can we divide by 6? Okay, well, the rule for 6 was it has to be divisible by both 2 and 3. So it has to be an even number, which they both are. So they both pass the divisibility by 2 test. But by 3, Well, 3 said add the digits together. So this one I'll get a 12. This one I'll get a 10. So only 12 can be divided by 3, not 10. So there we go. All right, 58 or 56, which one can be divided by 7? Again, an even division. 7 doesn't have a good rule other than it has to divide nice and evenly, and 56 does divide by 7 nice and evenly. 3160 or 3162, and we're trying to divide by 8. Well, the rule for 8 was if the last 3 digits form a number that we can divide by 8. So either a 160 or a 162. Well, if you think about it, 160 and 8, because 8 times 2 is 16. So 160 is going to divide by 8. 162 won't. So it'll be 3160. All right, 477 or 475. Divide by 9. Now, the rule for 9 was the sum of the digits has to be divisible by 9. Well, if I add up these digits, 4 plus 7 gives me an 18, and 4 plus 7 plus 5 gives me a what? 16. Which one can I divide by 9? I can divide that one by 9. All right, and then finally 182 or 180. We want to know, can I divide which one by 10? Okay, 10 is another easy one. It has to end in a 0. And there we go. All right, so it's, the rules are nice. They're clever. They're whatever you want to call them, but they can be tedious to remember, certainly. So, you can jump on the old calculator and accomplish the same task rather easily. Okay, but I'm not trying to dismiss the rules, but, they have their place. But our best friend, the calculator, does too. All right. Now we're going to talk about a thing called factoring. Okay, it's another thing we're going to have to do as we deal with fractions. Okay, we need to find factors. Okay, what are factors? Well, factors are numbers that are multiplied together to make another number. Okay, numbers multiplied. Okay, that's the key word, multiplied together to make another number. Okay, well, what does that mean? Well, if I say what's a factor of 18, say tell me the factors of 18. I'm asking you, what two numbers can I multiply together and get an 18? Okay, whole numbers, natural numbers now. Well, there's more than one possibility. You say, well, isn't 18 times 1 is 18, right? And 9 times 2 is 18. And 6 times 3 is 18, right? There's 3 possibilities here. Well, these are what we call factor pairs. Okay, pair because there's 2 of them, and they're factors. So the question right now is going to be list the factor pairs of, some number. Okay, in this case, 18. So we're going to list the possibilities. Okay, now how do we find those possibilities? Well, 18 we kind of knew, but what we really could do is go through all these divisibility steps with the 18. And can I divide by 4? Can I divide by 5? Can I divide by 7? Okay, that's a more methodical way to do it, is to run through all those examples, all those divisibility steps. Okay, that's kind of tedious. Let's just think about it. We can figure most of these out. Okay, oh, that was actually example 5, right? The factor pairs of 18, okay? Now, we're gonna do this factor pair where we're just listing all the pairs, but then eventually we're not really so much concerned with listing all the pairs. We're interested in taking one of those pairs, and it doesn't matter which one, and just keep working on that pair. And I'll describe more what I mean by that in a minute. But for right now, we're just going to find the pairs, okay? Find all the factor pairs, and then we'll take it up from there. So example 6 says, let's list all the factors, pairs of 48. Okay, so you just ask yourself, how do you make a 48? Okay, well, there's always 48 times 1. Just start thinking about it. It's an even number I can divide by 2. So 12 times 2 is 48. What about 3? I mean, some of these we might have to stop and think about a minute. Does 48 divide by 3? You know, if we're not sure, what do? We run over here and we say, First, we figure out how to turn the darn thing on. We say, oh yeah, it does. 16 times 3. Okay. Does it divide by 4? Okay, if we're not sure, we go over here and we check. Oh yeah, it does. Oh, I said 12 times 2, didn't I? That's not right. 24 times 2. 12 times 4. Okay, does it divide by 5? Now, we probably don't have to run to the calculator for that one because it has to end in a 5 or a 0. Divide by 6, we probably, yeah, 8 times 6 is 48, right? So, okay, 8 times 6. Will it divide by 7? Highly unlikely, right? Give it the old college try here. Nope. Will it divide by 8? Well, we already did that because we did 8 times 6. So now I'm just going to start repeating if I try that. Okay, so we've got it here. We've got it once we get to a duplicate. I did 8 times 6, and if I kept going, I would hit 8 times 6 again. So these are our possibilities now for the ways to factor. Boy, look at me. That's a 48. Ways the factor of 48. 48 times 1, 24 times 2. I'm losing it, man. 16 times 3, 12 times 4, and 8 times 6. Look at that. I'm going to pretend this page didn't exist. I got like 3 typos on the same problem. I will call them typos, not mistakes. Okay, everybody cool with that?
Yeah.
Yes.
How about if we wanted to do 28? Factor pairs of 28. Well, you can always do a number times 1. That's the one factor you can always do. Okay, maybe that's the only one, but that's the one for sure. 28 times 1, it's an even number. I can cut it in half. 14 times 2. Is that it? Anything times 3? Okay, I don't think so, right? Anything times 4? Oh yeah, 7 times 4 is 28, right? Times 5, no. Times 6, no. And now we're back at 7 again. So I think we've got them all. Okay. All right, we're going to want to do what we call a prime factorization. Okay, now what is that? Prime factorization. Well, what's a prime number? What's a prime number? A prime number is a number that can only be factored as itself times 1. Okay. So in other words, you know, the number, well, even the number 2. If I ask you to factor a 2, the only thing you can do is 2 times 1. If I ask you to factor a 3, 3 times 1. If I ask you to factor a 5, 5 times 1. And now you say, these are little numbers. Of course, there's no factors. They're too small. Well, you're kind of right there, but there's big numbers too that can't be factored, right? 7, we're getting bigger here. 11, 13, right? There's no way to factor any of these numbers. 19, okay, blah, 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 blah. There's a list of the first handful of prime factors here coming up in a minute. Okay, on the next page, at the very bottom of the page, it lists the first handful of what we call prime numbers, okay? Numbers that can only be factored by themselves times 1. These ones that are circled here, and the ones that are crossed out were weeded out in the process. 2, 3, 5, 7, 11, 13, 17, 19, 23, okay, et cetera, et cetera. You cannot factor any of those numbers other than itself times 1, okay? So that's what we call a prime number, okay? All the other numbers that I can factor, we call composite numbers. Yeah, I'll just say can be factored. Okay, and we're going to want to do that. We're going to want to take a composite number and we're going to factor it all the way down to primes. Okay, so it's helpful if you know the primes, if you can spot the primes. Okay, example 8 asks us to identify which one of these numbers are prime versus not prime. the number 4. You just ask yourself, can I break that 4 apart? Can I call 4 something times something? Well, yeah, 2 times 2, right? So that would have to be a composite number. Can I break a 10 apart somehow? Yeah, 5 times 2 is 10. That's a composite number. Can I break a 13 apart? No, I can't, right? So that would be a prime. Can I break a 12 apart? Yeah, I can break a 12 apart a couple of different ways. That's one way. So that's not prime. Can I break a 5 apart? No. So the 13 and the 5 were prime. The other ones are what we call composite numbers. Okay, so far so good?
Yes.
All right, we're going to want to take these composite numbers now and perform what's called a prime factorization. Okay, meaning I don't want to just find the factor pairs. We did that a little while ago, right? We found all the factor pairs. I don't want to do that. I want to just start somewhere with one of my factor pairs, and I want to keep factoring all the way down until I can't factor anymore. Okay, now the book's going to kind of do it in a horizontal fashion, if you will. I like to do it in a vertical fashion when we're just doing this prime factorization. Later, I'll switch kind of to the horizontal method also, because it's easier as we deal with these fractions. But when we're just doing these factorizations, I'm going to kind of, you'll see the book kind of goes horizontal, off to the side. I kind of go underneath. So we're asked to factor 30 there, okay? So you start somewhere, okay? Somewhere other than 30 times 1. Think of something else. Well, what can I do with a 30? Well, I could say 10 times 3 is 30, right? But then I keep going. I go to my 10 and I say, can I factor you, or are you prime? And we say, oh, 10 is not prime. 10 is 5 times 2. Okay, and then I ask myself the same question with 5. Are you prime? Yes, you are. So I'm going to circle it. Are you prime number 2? Yes. And yes. Okay, so once I get all the way to primes, that's what we call the prime factorization. Okay, so it's just a different way to write that 30. 30 is really the same thing as 5. And I'm just writing them in descending order, times 3 times 2. Okay. Let's do that. And if we have repeating factors, we're going to want to put them in exponential form also, because that's going to help us out in a minute, a little bit later. So part B says we'll do the same thing with the number 16. Okay. You may say 8 times 2 is 16. And then you say 8 is 4 times 2. And then you say 4 is 2 times 2. And you see, I got a bunch of 2's here. I can't factor a 2. I have 1, 2, 3. I have 4 2's here. So we say that 16 is really 2 times 2 times 2 times 2, but we want to write that as 2 to the power of 4. Is everybody good there?
Yep. Mm-hmm.
Now I decided to say 16 is 8 times 2. You may have said 16 is 4 times 4. You may have started differently, but you always get to the same place. Okay? 2 times 2 times 2 times 2. So it doesn't matter where you start. You're always going to get, if you're going all the way to primes, which is what we're doing right now, you're going to get the same answer. All right, 210 now, this next example. That's a little bit bigger, of course. So we might have to stop and think for a second, but the fact that we got a 0 at the end there, we can divide by 10. So that greatly simplifies things. So that would be a 21 times 10. And now it's much, much, much easier, of course. 21 we'll call 7 times 3. And 10 we'll call 5 times 2. And what do you know? 7 is prime, 3 is prime, 5 is prime, 2 is prime. So that 210 could be thought of as 7 times 5 times 3 times 2. All right, all good?
Yes.
Yeah.
All right, we're going to come back to factoring in a minute. But right now on the next page, our book is asking us to find something called the least common multiple. Okay, or LCM for, short. Okay, and then also we'll find the greatest common factor in a minute. So least common multiple. Well, what were multiples? Well, that's when I said, I've got, multiples of 3. 3, I count by 3. 3, 6, 9, 12, 15, 18, 21, 24, okay? And then let's say I want to find multiples of 4 also, okay? 4, 8, 12, 16, 20, 24, 28, okay? You notice I have some common numbers here. If we analyze here, I've got a 12 and a 12. If I keep scanning down here, I got a 24 and a 24. And if I kept going, I would have more matches. Okay. The least common multiple is the smallest match. Okay. So 12 and 12 is my smallest match. I've got other matches. I've got the 24s. And if I kept going, I would have more all the way down the line. But I'm interested in finding that smallest match, the least common multiple. Okay, least meaning the smallest, common meaning each one has the same number and it's a multiple of that number. Okay, so that's really one way to find it, what I just did there. And if the numbers are easy, like 3 and 4, that's maybe the quickest way to find it. Okay, but there's a more procedural, methodical way to find it here, listed in this green box on page 67. And here's what it says here. First, we got to do a prime factorization on each number. Now, 3 and 4 are both no-brainer factors. We'll pick some bigger numbers here to do this. We factor each number down to primes like we just did, okay? And then number 2, we gotta read it carefully. We list the prime factorization of the least common multiple. So we're gonna write down the least common multiple now by including the prime factors appearing in each number. Okay, so everybody's going to be represented. Every number we write as part of these factors, it's going to be part of our least common multiple, okay? But then if we have a number that has a repeated factor, so if we have an exponent, we're going to use the one with the largest exponent, okay? So, what does that mean? Let's just do it. Example set 10 says we're going to find the least common multiple of 12 and 40, okay? 12 and 40. So I need to factor my 12 down to primes. Okay, first of all. Start somewhere. 6 times 2, 4 times 3, doesn't matter. 3 times 2 is 6, and then I got a 2 there. So 12 factors into 3 times 2 squared. Okay, and the other number was a 40. Okay, 4 times 10. 2 times 2, 5 times 2. So the 40 factors into a 5 times 2 cubed. All right, everybody cool with that? My least common multiple says, okay, I got all these prime factors. Now everybody's going to be represented in the least common multiple. What does that mean? Well, I've got 2s, 3s, and 5s, right? 2s, 3s, 5s. So my answer is going to have 2s, 3s, and 5s. 2 times 3 times 5. It's at least going to be that. 2 times 3 times 5. Okay, but now I got to look at this note number 2 kind of carefully. If a prime factor appears in more than one number, use the factor with the largest exponent. So I've got a 2 squared, but over here I got a 2 cubed. So my answer, my LCM, is going to have a 2 cubed on it. All right, so if I now multiply these together, 2 cubed times 3 times 5, that's going to be the number I'm looking for. Okay, and in this case, it's 120. Okay, so that's kind of our procedure. How else could we have gotten there? 12, 24, 36, 48, 40, 80, 120. If I kept going, I would get a 120 down here, and that would be my first match. Okay, this is just a different way to accomplish that without having to write down all these multiples and search for a match. All right, let's try another one. Let's try the stop and check in the margin there. It says we've got these common multiples of 8 and 26. All right, so 8. 4 times 2 is 8. 2 times 2 is 4. So 8 I can think of as 2 cubed. 26. Well, all I can do with that is 13 times 2 is a 26. The least common multiple says, hey, everybody's coming along for the ride. So who's everybody? I got 13 and 2, right? 13 and 2. So it's at least going to be 13 times 2. But if I have anything with an exponent on it, I'm going to pick the largest exponent. So it's going to be 2 cubed. So 13 times 2 cubed, okay, which is 104. Okay, and then our other one was 9 and 26. 9 factors into 3 times 3, which is 3 squared. Okay, 26 we just did, 13 times 2. 9 equals 3 squared, and 26 equals 13 times 2. The LCM lets everybody come along for the ride. 13's coming, 3's coming, and 2's coming. Okay, and whoever has a high exponent, the highest exponent. So you notice in this case, it's everybody, right? I mean, truly everybody. 13, 2, and 3 squared, it's the whole thing. So in other words, if I would have just taken 9 times 26, I'm going to get 234. And that's, in this case, my LCM. Okay, you always get a common multiple when you multiply the two numbers together. You get a common multiple, but it's usually not the least common multiple. Okay, but it is a match. It's just down the chain somewhere, one of those matches that are way down there. In this case, it was actually our least common multiple. Okay with that idea, least common multiple?
Yeah.
All right, the other thing now is the greatest common factor. Okay, kind of abbreviated GCF. And remember, factors were those little numbers that multiply together to make the big numbers. So I'm going to have two numbers, and I want to search inside those two numbers to not only find a match, I want to find the biggest match. Okay, so the greatest, again, there's a procedure here, okay, and it involves doing your prime factorization just like before. But then when we're going to write this greatest common factor, not everybody comes along for the ride. Only the matches come along for the ride. And then if we have anything where we have different exponents, in this case, we're going to pick the smallest exponent. Okay, so in other words, if we just look at this example on the next page, we got 15, 30, and 45. We've actually got three numbers here. 15, 30, and 45, okay? You can see a 5 inside all those numbers, right? I mean, I know there's a 5 inside my 15. 5 times 3 is 15. I know there's a 5 in here, and I know there's a 5 in here, right? 6 times 5, 9 times 5, 3 times 5. So I know there's a common factor of 5, but is it the greatest common factor? That's the challenge. You can maybe spot common factors rather easily, but we're looking for the greatest one. All right, so to find that, again, there's a procedure. We'll factor down to prime. So 15 is 5 times 3. Okay, 30 we'll call 10 times 3, and 5 times 2 is 10. So 30, I'm going to say, is 5 times 3 times 2. And 45, I'll say 9 times 5 is 45. And 3 times 3 is 9. So 45, I'm going to say, is 5 times 3 times 3 again, or 3 squared. Okay. The greatest common factor says not everybody gets to come out and play here. Only the matches, only the common ones. Well, what's common? 5's common, okay. 3 is common, okay. 2 is not common. So 2 is not coming along for the ride. Only the 5 and only the 3. And then I examine my exponents and I put the smallest exponent. So 3 to the nothing means 3 to the 1, right? So that's 3 to the 1, that's 3 to the 1, that's 3 to the 2. So 3 to the 1 is what's coming. So that's, of course, 15. Okay, so in this case, my greatest common factor was actually one of the numbers to begin with. That's not always going to be the case. Okay, yes, there was a common 5 in here, but that wasn't the biggest. There's a common 15 in all those numbers. And now you can see it, right? 15 times 2 is 30. 15 times 3 is 45. 15 times 1 is 15. So you can see it in there. All right, let's try 10, 12, and 13. Greatest common factor, 10, 12, and 13. Well, 10 is 5 times 2. 12 is 6 times 2, which is 3 times 2 times 2. Let me write it here. 10 equals 5 times 2. 12 equals 3 times 2 squared. I should make a habit of circling my primes here. Now 13, right? It's nothing there, right? 13 times 1 is all I can do there. So 13 is just 13. So I'm almost going to call this a trick question because I'm looking for common factors. I'm looking for the greatest common factor, and there's not even any common factor, right? 5 is not represented everywhere. 3 is not represented everywhere. 13 is not represented everywhere. 2 is not represented everywhere. There's nothing represented everywhere. Okay, so there's really no greatest common factor for this one other than 1. I mean, we can say all of them have times 1. I mean, I would say there's really no greatest. I mean, no is not exactly proper to say, okay, but 1 is the only thing I can do. Okay, I can always say, oh yeah, times 1, times 1, times 1. 1 is common. Okay, but there's really nothing common between them except a 1. All right, let's try those couple in the margin, and then I think it'll be time for a little break. Let's what do we have? 48, 18, and 30. The first one. Looking for the greatest common factor. Okay, think about it. What's hidden inside? Well, I know there's a 6 inside my 48. I know there's a 6 inside my 18. I know there's a 6 inside my 30. Maybe the answer is 6. I'm just guessing. Okay, let's work it. Well, 8 times 6 is 48. 4 times 2 is 8, and then 2 times 2 is 4. So, oh, and then 6, I'm not done either. 3 times 2 is 6. Okay, so look at all these. 48, what do I have here? I'm going to get lost. I've got 3, and then I've got 4 2s times 2 to the 4th power. Okay, 18, what do we have? 6 times 3, 3 times 2. So 18 has got 3 squared times 2. 30, 10 times 3, and maybe I'll say 5 times 2 is 10. So 30 has got 5 times 3 times 2. Okay, the greatest common factor is exclusive, right? You gotta be everywhere, otherwise you can't come out and play. So we need a match everywhere. Do I have a matching 3 everywhere? Yes, I do. So 3's in here. Look at the exponents. I have an exponent of 1, 2, and 1. I picked the smallest, so just the 3. Okay, 5 is not everywhere. 2 is everywhere, and it has an exponent of 1 is my smallest, so it's just going to be 3 times 2. So greatest common factor is 6. Okay. All right, let's take a little break, and then is 5 minutes enough?
Yeah.
Okay, I'll see you back at 8:30.
Okay.
All right, let's do it. So let's dive into our next section here, equivalent fractions and decimals. Equivalent fractions are just fractions with different denominators. Okay, but they have the same value. Okay. In other words, I like to do the old pie chart example when I talk about this. If I draw the old pie chart here, the old pie, and I shade this in, how much have I shaded?
Half.
Yeah, duh, right? Half. Okay. So we all agree this is half. Okay, well, if I break out my knife and I slice the pie again, all of a sudden that half is not half anymore. It's 2 out of 4. Okay, but we know it's still half. We just think of it as 2 out of 4 instead of 1 out of 2. Now we can think of it as 4 out of 8. Okay, 1 out of 2 is the same thing as 2 out of 4 is the same thing as 4 out of 8. Okay, we just know those to be half from everyday life. 50 out of 100, we know it's half. 500 out of 1,000, we know it's half. They're all the same. Okay, if you stick it in the old calculator, you get a decimal of 0.5, right? 1 divided by 2, 0.5. 500 divided by 1,000, you get the same thing, 0.5. Okay, so equivalent fractions are just reslicing the pie, okay, but the amount of shaded material doesn't change. Okay, in all these cases, I didn't change what I shaded, I just played around with the slicing and I just did one of these maneuvers. And I made it look a little different, but I kept the same amount shaded. And that's what an equivalent fraction is, okay? Different denominators, but the same amount of shaded material, the same value. So these are all what we call, the same family. And they're all the same value. So if we want to find some equivalent fractions, the way we can do that, you say, well, how do you go from 1/2 to 2/4? I mean, what's the procedure here? If I just ask myself, how in the world would I start with a 1/2 and turn it into a 2/4? You just say, well, what if I multiply by 2 and multiply by 2? 1 times 2 is 2 and 2 times 2 is 4. That would do the trick, right? Or how would I go from 1/2 to, 4/8? How would I do that? Well, you'd say, well, you got to multiply top and the bottom by 4. That'll do it. Okay. Well, let's think about what I've done here. I've multiplied by 2/2, or I've multiplied by 4/4. What's the value of 2/2? It's a 1. What's the value of 4/4? It's a 1. So I'm really only multiplying by 1, and we all know when you multiply by 1, nothing happens. Same thing, but it doesn't look like a 1. We make it look a little different. It looks like a 2/2 or a 4/4 or a 50/50 or whatever. Same thing, top and bottom. It's 1. Okay, and that's how I can reslice these pies here by multiplying by the same number, top and bottom. Okay, and that's what example 1's asking us to do here. Take this fraction we call 1/2 and find 5 equivalent fractions. Now they just pick whatever numbers. We can pick our own numbers. We can multiply by 6/6, and what will that give us? 6 out of 12. We know that to be 1/2. Multiply by 8/8. What's that going to be? 8/16. We know that to be 1/2. Now you see, I can think of it as a top and a bottom, or I can think of it as a fraction times another fraction. We'll get to this. Let's call it 10/10. So it's like the fraction 1/2 times the fraction 10/10. And when you multiply fractions, You multiply the numerator, 1 times 10 is 10. You multiply the denominator, 2 times 10 is 20. And that's how we would convert 1/2 into 10/20, okay, half. All right, all good there? So we're gonna multiply by, in the gold box there, the yellow box, some n over n, okay, which has a value of 1. Okay, and in the world of fractions, we can never, ever, ever have a denominator of 0. So you see the little caveat there. N is not allowed to be 0. Okay, we can never divide by 0. So we can never have a denominator of 0 in the world of fractions. Otherwise, it's fair game. N is some number. Going to multiply the top and the bottom of that fraction by the same number and turn it into an equivalent fraction. Okay, so if I want to go from a quote unquote small fraction to a big fraction, same value, but if I want to take 1/2 and turn it into 500 over 1,000, when I say small and big, that's what I mean. It's the same value. Okay, well, I'd have to multiply by 500 top and bottom, and that'll give me 500 over 1,000. Okay, so it's a process of multiplication. I multiplied by 500 top and bottom. What if I want to go the other way? What if I have 500 over 1,000 and I want to go the other way? Well, I can simply divide the top and the bottom by 500. Okay, and that'll give me a 1 over 2 again, 1/2. Okay, so we can multiply the top and the bottom of a fraction by a number. We can divide the top and the bottom of a fraction by a number. It's got to be the same number both times. Okay, because it's going to give me a value of 1 when I do that. All right, well, how do I know? Well, sometimes you got to figure it out. I mean, if I want to take 1/2 and I want to turn it into something with denominator 60, well, you got to stop and think, how would I turn that 2 into a 60? Multiply by 30, right? So I've decided now. I'm going to multiply top and bottom by 30. Well, how did I decide? Because somebody gave me that 60. So that's the only way to do it. 2 times 30 is 60. 1 times 30 is 30. All right, so as we create these equivalent fractions, sometimes that denominator is going to be known, or we're going to say, aha, this is a denominator for me. I want this denominator. How do I get there? Well, I'm going to multiply by some number to get there. Okay, example 2 is going to do just that here on the next page. It says take 5/8 and work your magic and give me a denominator of 32. Okay, example 2 here. Well, you got to figure it out. Now, how are you figuring it out? You're thinking it through, or more procedurally, you're saying, what the heck is 32 divided by 8? That'll give me the magic number of 4. Okay, 4. Multiply by 4. Always do the same thing, top and bottom. 20 over 32. All right, in the margin there, it says, let's change 5/6 into an equivalent fraction, and I want 42 in my denominator. Okay, so now, again, the challenge is, how do you turn a 6 into a 42? We're going to multiply by something, by 7, right? So it's going to be the fraction of 7 over 7. 7 times 5 is 35. 7 times 6 is 42. We are saying that 5/6 equals 35 over 42. Okay, they're the same. All good?
Yeah.
Yeah.
Good. A lot of times we want to go the other way, though. We got this big old fraction. We want to, what we call, reduce the fraction. Okay? Reduce to what we call lowest terms. Reduce to lowest terms. Okay, so that means you're going to start with, I'm using the word big and small. They're the same value, but we're going to start with the unsimplified, larger, clunkier looking fraction, and we're going to make it as simple as I can get it and still be the same value. Okay, I'm going to take, the 25 over 30, and I'm going to do so. I want to simplify it. I want to do what's called reduce it. Okay, I want to divide through the top and the bottom of this fraction by the greatest common factor. Okay, now we can probably spot right now that there's a factor of 5 common to both this 25 and this 30. So if we just play around with 5 and we say, let's divide by 5 and let's divide by 5. Well, 25 divided by 5 is 5. 30 divided by 5 is 6. And, that happened to do the trick in this case, okay? We kind of guessed at the greatest common factor and found it. And that's how you can simplify these fractions. Find the greatest common factor and divide through by it, okay? Now here's the book and I are going to differ a little bit on strategy here. And there's absolutely nothing wrong with what the book is going to do here. I just choose to do it a little bit differently. But let's look at this example 3. So let's reduce 8 over 10. Okay, the procedure in the green box right above there that I didn't read says, first of all, find the greatest common factor. Okay, divide. Okay, it says find a factor. Okay, divide, and then we might have to continue this process. That's okay. That's a little better than finding the greatest common factor. If we find the greatest common factor, you can knock it out in one shot. Okay, the advantage of finding the greatest common factor is once you've found it, now you're practically done. Okay, so let's do that real quick. Find the greatest common factor of 8. How do we do that? 4 times 2 is 8. 2 times 2 is 4. So an 8 can be factored as 2 cubed. And a 10, 5 times 2 is 10. So it's just 5 and a 2. So a 10 is 5 times 2. Remember, the greatest common factor said we're only going to pick the common numbers. So only 2 is common. 5 is not common. And we go with the smallest exponent. So it's just a 2. Okay. The problem with this is it took a little legwork to figure that 2 out, right? I mean, look at all these steps I had just to figure out the 2. But now that I've got the 2, now there's one step. 4 over 5. Okay. The way I prefer to do it is not take this time to find the greatest common factor. I just say, okay, 8 over 10. Let me factor my 8. Now here's where I'm going to start factoring horizontally. 4 times 2 is 8. Let me factor my 10. 5 times 2 is 10. And you can see I've got this 2 over 2 here, which divides into a 1. Okay. We use the word cancel a lot. Okay. And we cross them out, cancel. Okay. But what that means, they don't disappear. They don't turn into zeros or something like that. They divide away. 2 divided by 2 is 1. And 1 times whatever is the same whatever. Okay. So we cross them out and say cancel. Okay. But that's the process. It's a process of, hey, something divided by itself is 1. 1 times whatever is left over is still whatever is left over. And that's how we're going to reduce. Okay. So this factor and cancel, factor and cancel, factor and cancel is a quicker way than finding the greatest common factor. Okay, because it takes a little effort to find that greatest common factor. Okay, let's try one more that way. Example 4, we've got 18 over 24, and we're supposed to reduce it. Okay, well, the book says let's find the greatest common factor, right? So let's say, how do you factor in 18 here? 6 times 3 is 18. 3 times 2 is 6. Okay, so this 18 factors into 3 squared times 2, right? Now I got to do a 24. I say 8 times 3 is 24. 4 times 2 is 8, and 2 times 2 is 4. I forgot to circle on my little primes here. So what is a 24? It's 3 times 2 cubed. Okay, so my greatest common factor is only the common ones. I have a common 3 and I have a common 2, so it's at least 3 times 2. But then I'm looking for smallest exponents, so it's 3 times 2, so it's a 6. And I'm sure you already knew there's a common 6 in an 18 and a 24, but here we've identified the greatest. There can be nothing else, okay? And once I do this next step now, which says divide by 6 and divide by 6, I'm going to be done. 3/8. I can't do anything else. 3/4. Okay, I can't do anything else. Done. So the legwork to find this takes time, but then boom. Here's what I would do. You asked me to reduce 18 over 24. I start chipping away at it. I say factor my 18. Now maybe I'm going to say 9 times 2 is 18. Up here I said 6 times 3. There's lots of ways to factor, right? Here I'm going to say 9 times 2. And I'll say 12 times 2 is 24. And you see I've got a common 2 there I can knock out, but I'm not done. Okay? It takes steps if you don't catch the big factor first, okay? But I didn't catch it, let's say. Oh, well. I keep going. 9 is 3 times 3. 12 is 3 times 4. Now I can knock out the pair of 3s, and you see I'm at 3/4. Okay, so it just depends. Maybe I would have got lucky, or maybe I saw it, and maybe I said, hey, 6 times 3 is 18. 6 times 4 is 24. Bada boom, bada bing. I'm done. Okay. Maybe I would have even done a step that didn't help me at all. Maybe I would have on the 18. Maybe on the 18, I would say 6 times 3 is 18. But then I would say 12 times 2 is 24, and nothing cancels, right? What a waste that was, seemingly. Well, I'm working it. I'm getting there. Nothing cancels, correct, but I'm just going to keep going. 3 times 2 is 6, so I have 3 times 2 times 3 on the top. And now down here, you know, what can I do? 4 times 3 times 2. 2s are going to cancel. 3s are going to cancel. I'm left with 3/4. Now, you may say, and it's good. It's a good thought if you said this. You may say, well, don't you got to factor that 4 and call it 2 times 2? Well, it's a good thought, but you can see that 2 is not going to cancel. So it really didn't do anything in this case. It's good thinking, like I said, to explore, because maybe there was an extra 2 up here, in which case I would have to knock out a pair of 2s. But in this case, no. So I'll just leave it as 3/4. Okay, so that's kind of my preferred way to do it. Now, what if we had 25 over 30ths, which I think we did a minute ago, and we said, we got to divide top and bottom by 5 because we identified it. Well, if you just go the factor route, 5 times 5 is 25. 5 times 6 is 30. Out we go. 5, 6. What if I have something like, 6/18? Okay. Now you may say 3 times 2 is 6, and then you may say 9 times 2 is 18, and you might cancel those 2's out. Okay. And you'd say, well, 3 is prime, so I can't factor him anymore. He just stays there. But 9 is 3 times 3. And then you might be in this little predicament where all of a sudden there's nothing left on the top. Okay. And you might, I'm not going to accuse you of this, but you might say, oh, well, then I guess the answer is 0 because there's nothing left on the top. Okay. The answer is never 0 when you're factoring. Remember what we're doing. We're taking this thing we call 6/18 and we're just re-slicing the old pie there. How could it be 0? It wasn't 0 to start with. So here's where you got to remember, oh yeah, 3 really means 3 times 1, right? There's always a times 1 there. So the answer is really 1/3. 6 out of 18 is 1/3, right? 6, 12, 18. So eventually you could run out of factors to cancel and you have nothing left up there while you always have a 1 left up. Okay, it's never 0 when you're reducing a fraction. Okay, so where the heck were we? It was example 4. I think I snuck a couple extra things in there. That stop check in the margin says 30 over 45. Okay, again, we could do the prime factorization of both and find the greatest common factor and then divide through by it, or we could just say, think about it. What's common between a 30 and a 45? At least the 5 has got to be common, right? 5 times 6 is 30. 5 times 9 is 45. That wasn't the biggest, but it was something, right? Chip away at it. Goodbye 5s, and now I'm left with a 6 over 9. So now we can see a 3 hidden inside there and a 3 hidden inside there. And we can cancel those common 3s and be left with 2/3. Everybody cool with reducing a fraction? Factor, cancel, factor, cancel, factor, cancel.
I'm gonna need some more practice on this one. I'm sorry. I have to be honest.
Okay. Well, let's
Maybe I
see.
need to study my multiplications. I think that's what that's what it is.
Am I losing it when I do these factors? Where am I losing?
Click.
Pardon me?
Oh, I think that was somebody else, but I'm not really. I think the steps. That's probably what it is for me. Is this? I'm like a person who have a hard time with steps. So, I mean, can we do one more?
Absolutely. Let's do, let me just think of something here. What can we do? Oh, whatever. Let's just do, let's do 14 over 48. I'm just making that up. What's common? Well, what can I factor? Just start breaking stuff apart. 14 is 7 times 2.
Right.
And 48, I could say, is 24 times 2. And the 2's are gone. Well, this one might not have been a great example because we're done, but we'll do another one. Well, the next step would be to say, can I cancel that 7 somehow? Is there a 7 hidden inside my 24? Maybe you'd even start factoring the 24 and say 8 times 3 is 24, but nothing's going to cancel here, right? So we would leave it as 7 over 24. Let me think about it. What else can we do? I don't know. Let's do I don't know. What's a good one? What's a good one? Are there any good ones? Let's do 64 over 80. I don't know. 64 over 80. They're both even. Okay, so worst case, if we can't come up with anything better, I could divide them both by 2. I can factor a 2 out. So 32 times 2 is 64. 40 times 2 is 80. I can at least do that much. Goodbye 2s. So now I'm left with a 32 over 40. I could divide by 2 again. They're still both even. I could go 16 times 2 is 32. And 20 times 2 is 40. Goodbye another pair of 2s. They're still both even. Okay. Cut them in half again. I could get 8 times 2 is 16. And 10 times 2 is 20. Goodbye another pair of 2s. All right. You can see I'm still even here. I can cut them in half again. 4 times 2 is 8, and 5 times 2 is 10. Goodbye another pair of 2s. In this case, all the common factors were 2s, but we worked our way through it. You factor and cancel, factor and cancel. So 64 over 80 can be simplified as 4/5. Does that help?
Yeah, I did. Thank you so much. Sorry.
Awesome. Okay. So what if somebody tried to pull a fast one on us and said, you know what? 5/8 equals 15/24. You know, I'm making this big bold claim. 5/8 equals 15/24. Well, how do we know if we can believe it? You know, how do we really know that's true? Well, so we might want to check. You know, we're going to check. Of course, you can always check when you're doing these two. You can check your answer. There's a couple ways to check. 3 ways, really. Number one, it's a fraction is a division problem. Yes, we can take good old 5 divided by 8. It's going to be some decimal, 0.625. I better get the same decimal when I take 15 divided by 24. Otherwise, they're not equal. And I did, 0.625. So that's one way of checking. Okay. Another way of checking is by matching denominators. If I have the same denominator, then I better have the same numerator. Otherwise, it's not the same fraction. So I could ask myself this question. Well, if I had to turn an 8 into a 24, it would be a process of times 3, right? 8 times 3 is 24. 5 times 3, 15. Okay, so I'm digging it. I like it. Okay. Yet another way to check is to do what we call cross multiply. Okay, if I take the 5 times the 24, it has to equal the 8 times the 15. Okay, if it doesn't, then something's wrong. Okay, so if I take 5 times 24, I'm going to get what? What am I going to get here? 5 times 24, 120. Okay. And if I take 8 times 15, I better get that same 120. And I do. Okay, so these are all ways to check. Match the denominators, and then the numerators have to match, because then it's the same fraction. Perform the division. You'll get a decimal and make sure it matches the other decimal, or do this thing we call cross multiply and make sure they're really equal. So if you look at the next page here on what is it, 72, there's that in the green box. It kind of explains, what's going on here in symbols. If some A over B equals C over D, if we do this thing called cross multiply, it has to also be equal. Okay, so that's what I just did the first one of example 5 there. Okay, let's do the second one. We have 6 over 9, supposedly equals 10 over 15. We're verifying whether or not this is true. Well, if I take this cross product of 6 times 15, it has to be the same as 9 times 10. Otherwise, I'm in trouble. 6 times 15 is 90. 9 times 10 is 90. So, this one checks out. All we're doing is checking here to see if it's really true. All right, what about this third one? 9 over 12 supposedly equals 12 over 18. Well, if so, then my cross product better be the same. 9 times 18 better equal 12 times 12. Otherwise, something's up. Well, 9 times 18 is 162, and 12 times 12 is 144. So guess what? No, not equal. So an equal with a slash is not equal. Okay. All right. So when we look at the old ruler, we got all those little hash marks in between the big inch increments of inches or whatever. We got all those little marks on the ruler, all these little in between hash marks there. Let's see, is that gonna focus? Not really. It's probably just as easy to look at the book. In between, like the 1 and the 2, for example, you see on this ruler, there's 16 little hash marks there. Okay. I've got my big old ruler here. This is the number 1. And this is the number 2. If I draw it kind of how they draw it, I'm not going to attempt to completely recreate this, but there's 16 marks in there. You see they're kind of have like different lengths. 1, 2, 3, and then the 4th one's even a little longer. 4, 5, 6, 7, and then the 8th one's even longer. 8. I'm getting this wrong. I'm getting this totally wrong. That's okay. 9, 10, 11. That one's kind of like that one. 13, 14, 15, and then this one would be my number 2. So forget about all that. Okay, so standard ruler's got these little hash marks in here. So in between the 1 and the 2, you know, that's like our whole number. Whole number 1 and whole number 2. Well, guess what's in between the 1 and the 2? We got all these little fractions in there. This first fraction would be 1 increment out of 16 total increments, right? So it would be 1/16. That first little increment is 1/16. Now the second little increment, I'll write it underneath here for space. We would say, well, that's got to be 2/16, right? Well, yeah, it is 2/16. However, 2/16, I can factor that as 2 times 1 over 2 times 8 and cancel my 2's, and it's really 1/8. So we would want to write it, you know, simplified as 1/8. So if you look over here in the margin where it's nicely done here, 1/16, and the next one, instead of 2/16, that's 1/8. Well, the next one is 3/16. Okay. Well, this next one you would say, well, that's got to be 4/16, right? Well, yeah, it is. But what's 4/16? You know, 4 times 1 is 4. 4 times 4 is 16. Goodbye 4, that's just 1/4. So we'll call it 1/4 instead. Always use these, what we call the lowest terms, the simplified. So if you're counting in increments of 16ths, it's 1/16, then it's an 1/8, then it's 3/16, then it's a 1/4. 5/16 will be next. Okay, and then you would say 6/16 is the next one, but again, 6/16. 3 times 2 is 6. 8 times 2 is 16. Goodbye 2's, and I'm left with 3/8. Okay, so that's really a 3/8. Yeah, it's a 6/16, yes, but 3/8 is the simplified way to state it. 7/16. You know, if you know anything about not only increments on a ruler, but you know, tools and wrenches and all that stuff, you know, these sizes should ring a bell. 7/16, 5/16, 3/8. These are all the common sizes. This next big one now would be 8 out of 16. Well, we know 8/16 is just a good old 1/2, right? 8 out of 16 is a half. So again, 1/2 there. So they're kind of showing as we go here, you know, the ones that have the denominator 16 have these really little short hash marks. The ones that have the denominator 8 are a little bit bigger. The 4th are a little bit bigger. The half are a little bit bigger. That's just a nice visual for as you're looking here and counting hash marks. It's kind of a nice visual for you to read it a little better instead of having to count every little hash there. All right, but what's after 8/16? Well, that would be 9/16, right? We're just counting the 16 is all we're doing here, and we're simplifying if we can. 9/16 I can't simplify. 10 out of 16 I can though, right? 10/16, what the heck is 10/16? Well, 5 times 2 is 10, and 8 times 2 is 16, so that'll be 5/8. 11/16 I cannot simplify. 12/16 I can simplify, right? 12 out of 16. 4 times 3 is 12. 4 times 4 is 16, 3/4. 13/16, can't simplify that. 14/16 I can simplify, right? 14 out of 16. 7 times 2 is 16, and 14. 8 times 2 is 16, 7/8. Okay. 15/16. And then that next one would really be 16/16, right? Wow, 16/16, you know, you can just think of that as cancel, cancel, or it's 1. In other words, I've made one whole increment step between the number 1 and the number 2, and that's one whole, right? So there we go. All those little hashes on the ruler are these increments here. Okay, and that's why they have different denominators, because we're just reducing where we can. But that's how we would count all those little hash marks there. All right, so if we want to read this ruler now in example 6, measure this line segment, which we're calling AB, the line segment AB. Well, you look at the ruler and you say, Well, it's hole number one, it's hole number two, so it's 2 inches and a little bit more. And how much more? We start counting. 1, 2, 3, 4, 5. There's 6 of those increments. So it's going to be 2, and we got to talk mixed numbers here, which we will, but 2 and 6 out of 16, but 6 out of 16 was one of those we can simplify into 3/8. So we call it 2 and 3/8. Okay, everybody cool with that one?
Yeah.
Yep.
Like
Yeah,
it.
we're good.
Sweet. I like it. Well, let's do the one on the next page. And now sometimes you're going to be in between increments and you got to just give it the old eyeball judgment. Now this next one, if you see the line segment CV there, well, it's past the 1, obviously. It's not quite to the 2. So if you start counting hash marks there, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It's between 13 and 14. So it's between 1 and 13/16, and then we would say 1 and 14/16, which is really 1 and 7/8. So it's somewhere in between those two. So you'd either, I guess, pick the one that's closest, or if you could visually cut every one of and put an extra hash mark in between every one of those, now you got a denominator of 32 instead of a denominator of 16, right? And you can start counting by 30 seconds. And you'd be a little bit closer. You'd be somewhere in the middle of those two, but now we're going beyond the scale that's shown on the ruler. So probably best just to pick one of these two, whichever one you think it's closest to, as far as your answer goes. Okay. All right. So remember these improper fractions, they have the larger numerator over the denominator. That was the larger over the smaller. And if it's a large number divided by small number, it's something bigger than 1. Okay, so we can express that as what we call a mixed number. We've kind of just been seeing those mixed numbers right there. So we can turn an improper fraction into what's called a mixed number. Okay, now example 8 turns out there is no mixed number required in example 8 because it's going to be a nice whole number. Okay, 15/3, that's the division problem. 15 divided by 3, it's just a good old 5. We don't have to worry about it. Okay, and then if we did the old longhand division, right, we'd say 3 goes into 15 5 times. 5 times 3 is 15. We subtract and we get that remainder 0. So that means it's a whole number, nothing to worry about. When we get these mixed numbers, we're going to have a remainder. Okay, and that's the remainder is going to give us this mixed number part of the number. All right, so if we check out our next example, we're going to see that, I think. Example 9 says, right, 28/8 is a mixed number. Okay, so 28/8, it's a division problem. Take 28 and divide it by 8, right? Well, how many times does 8 go into 28? 8 times 3 is 24, right? Subtract and we get this remainder of 4. Okay, so way back in the day, we used to say 3 remainder 4, right? Well, we can't get away with that anymore. What does that really mean? It means there's the whole number 3, and then there is the fraction of 4/8. So my remainder over my divisor out there. 4/8, and of course 4/8 can be reduced. We always want to reduce. 4/8 is a half, right? So 3 1/2. And so that's what we're going to want to do with these guys. We're going to want to perform the division, and then my remainder becomes the numerator part of the mixed number, and the number I was dividing by becomes the denominator. Okay, let's try a couple others. Let's try 62/5, that's in the margin there, 62/5. So I'm going to perform this division of 62 divided by 5. 5 goes into 6 one time, right? 1 times 5 is 5. Subtract and I get a 12. 5 goes into 12 2 times. 5 times 2 is 10. I got this remainder of 2 now. So my answer is going to be the whole number 12 and then 2/5. Okay, how about 38 over 6? Well, 6 goes into 38 6 times, because 6 times 6 is 36. Subtract and I get a remainder of 2. So we would write down 2 and 2/6, but then we always got to reduce. 2/6 I can reduce to 1/3. So there we go. Okay. All good there. There are times when it's beneficial to turn a whole number into a fraction. Remember fractions rule, right? Don't forget it. They do. So even if we have good old number 5, I might want to think a good old number 5 is a fraction, so I'm just going to slap a denominator of 1 on it, okay? Can I do that? Yes, because what does that mean? It means 5 divided by 1, and last time I checked, that was still a 5, right? So I can always slap a denominator of 1 over any number, 8 divided by 1, anything divided by 1. I can turn a whole number into a fraction if I want to, okay? I can turn a whole number into an equivalent fraction if I want to. 5 over 1, I could say, just for laughs, let's multiply by 2 over 2, and I'll call that 10 over 2. 10 over 2 is 5, but maybe I want to think of it as 10 over 2 instead of thinking of it as 5. Okay, so I can always turn any whole number into a fraction with denominator 1, and then I can turn it into an equivalent fraction just as easy. Okay, there'll be times when we want to do that. So that's example 10 is asking us to do that. Change the number 8 into something over 5. Change the 8 into something over 5. Well, that's 8 over 1. And I want to change it into something over 5. So I ask myself a question here. How did that 1 become a 5? Well, I said times 5 top and bottom. That's how. So it's 40 over 5. Okay, which of course we know to be 8. So I can change the whole number 8 into the fraction 40/5 if I feel like it. Okay. Everybody cool there?
Yep.
Right. How about changing a mixed number back to an improper? Now we went from improper to mixed, right? By performing the division. How about if I go the other way? What if I have 6 and 2/3, and I want to turn that into an improper? Well, the procedure is, and I think it's at the top of the next page, but the procedure is you take the denominator times the whole number. So this is going to be, denominator times the whole number, and then I'm going to add the numerator, and that's all over the same denominator. So 6 times 3 is 18, plus 2 more is 20. So I'm going to get 20 over 3. Okay. Take denominator times the whole number, which order of, I didn't really have to have this parentheses because order of operations would tell me I have to do that first, and then I add the 2, and then I divide by 3. Okay, let's do a few more. Let's do 5 and 4/5. 5 times 5 is 25, plus 4 more is 29/5. Okay, 7 and 8/9. 9 times 7 is 63, plus 8 more is going to be 71 over 9. Okay, everybody okay with these? So the top of the next page kind of shows a little graphic, if you will, on how to do that. We've just done a few. Denominator times the whole number plus the numerator, all back over the same denominator. I don't know if the visual is helpful or not, but if it is, there you go. Okay. Well, turning a fraction into a decimal is no problem because that you just divide the numbers, right? We've already done some of that. But how would I turn a decimal into a fraction? How do I take this number, 0.4, and turn it into a fraction? Well, if it's a number like that, how do we read that number? How would I pronounce that number? That's what we would call 4/10, right? So that kind of tells you the fraction right there. 4/10 is 4/10, 4/10. Okay. Yeah, well, how did I do it though? Well, talk to me. How did I do it? Well, I said, give myself a denominator of 1. And then I said, how can I turn this 0.4 into just a 4? Because a fraction should be a whole number over a whole number. Well, I would have to multiply by 10 to make that happen. And I got to multiply by 10 on the bottom too, so we're nice and even. 0.4 times 10 is 4. 1 times 10 is 10. And that's how we can do that. Okay, so I'm just going to multiply top and bottom. It's like an equivalent fraction again. Okay, I'm going to make kind of a weird looking fraction because it's got a decimal in there, and usually we don't associate fractions with having decimals in it. It's a nice whole number, top and bottom. Okay, but we're going to kind of temporarily make a goofy looking fraction with the decimal there. Okay, like that one. I'm going to slap a denominator of 1 underneath it, and then I'm going to say, I would need 1, 2, 3 decimal shifts to turn that into a 75. 3 decimal shifts means times by 3 zeros after that 1, or 1,000. Because it's a fraction, I have to do the same thing top and bottom, right? So it's really like I'm multiplying by 1. It just doesn't look like a 1, but it is a 1. And then that'll give me a 75 on the top and 1,000 on the bottom. Okay, and we would read this number 75 1,000ths. That's how we would read it. We would read that one 4/10. Okay, you can see it in the fraction how you would read it. Okay, now what about part C here though? 3.17. Now if I follow my same logic here, slap a denominator of 1 under it. Okay, ask myself, what does it take to make it a whole number? 2 powers of 10, so times 100. Same thing top and bottom. 317 over 100. Okay. Yes, it's a fraction now, but it's an improper fraction, which we kind of frown on those. We want to turn those into mixed numbers. So the way I'm doing it now is kind of like the hard way. First, I turned it into a fraction, but now what do I got to do? I got to go through this procedure here of saying, oh boy, what's 317 divided by 100? Well, how am I going to do that? Well, it's going to be 3. Okay, and then I subtract and get this little remainder of 17. So it's going to be the whole number 3 and the fraction of 17 100ths, right? Well, that was kind of the hard way. The easier way is to say, hold it, wait a minute, hold it. We were asked to take 3.17 and turn it into a fraction or a mixed number. Well, this 3 is the whole number part. So that's really, if I want to spell it out, 3 plus, trying to show both of these together, plus 0.17, right? That's what 3.17 is. So in other words, the 3 kind of can leave the 3 alone. We only need to focus on the 0.17 part. Okay, so we'll get back to the 3 in a minute. 0.17, I'll slap a denominator of 1. I'll say, how do I make that a whole number? Oh yeah, times 100 times 100. So that's really 17 over 100. So I had 3 plus 17 over 100, which a mixed number is an addition problem. Okay, here, this is the one time in math where you don't see a plus sign, even though it's a plus problem. There's a lot of times in math where you don't see a multiplication sign, but you're multiplying. There's other symbols there. In algebra, you have no symbols. Even we had some that, we said area is, length times width, and we didn't put anything between the L and the W. It's implied that there's a time sign there. We're supposed to know that. Well, really, with a mixed number, there's a big old ugly plus sign in here. We just don't write it. That's what we're saying. It's 3 plus 17 over 100. It's not 3 times 17 over 100. Okay, but for whatever reason, this convention we call mixed numbers said, yeah, but we don't have to show the plus sign. But that's what it means. Okay, so when I wrote it out here, 3 plus 0.017, that's what this is. A mixed number is really an addition problem. We just don't show the plus sign. Okay, so the takeaway from this one is it was a number bigger than 1, so we leave the whole number part out because it's just going to be the mixed number whole number. Okay, it's still there. We only focus on the decimal part. So let's try those ones in the stop check in the margin there. Let's try those. We've got 0.21. Okay, the question says write it as a fraction or a mixed number. Okay, or we'll slap a denominator of 1 under it. That's a fraction, but it's not, we don't like it. We want whole numbers. We don't want decimal fractions. So you got to ask yourself, well, what would turn that 0.21 into a whole number? I got to multiply by 100. In the world of fractions, when we're playing around like this, we got to do the same thing top and bottom. Otherwise, we've destroyed it. It's not equivalent anymore. It's always got to be equivalent. We're just reslicing the old pie here. Now it's 21 pieces out of a 100-piece pie. Instead of 0.21, it's 21 out of 100. 21 hundredths. Okay. 0.06. Again, slap denominator of 1. I still need to multiply by 100 with this one also. Gives me 6 over 100. Which I can reduce. 21 over 100 I could not reduce. 6 over 100 I can reduce. I can say 3 times 2 is 6. And I can say 50 times 2 is 100. And I can knock those 2's out of there. 3/50. Okay, and finally 6.033. Turn that into, in this case, it'll be a mixed number. Okay, so I would just kind of remember the 6. Let's forget about the 6 for a minute. Call it 0.33. Figure that out, and then we'll put the 6 back in. Give it a denominator of 1. We got to go 1, 2. I need 3 decimal shifts. That means 1,000. So it's really going to be 33 over 1,000. Okay, but I had that whole number 6 in front of it. 6 point that. So it's the mixed number 6 and 33 over 1,000. Okay. Fraction to decimal, bust out the old calculator. That's easy. Divide. How do you change 7/8 to a decimal? Well, what does that mean? It means 7 divided by 8. Bust out our best friend here. 7 divided by 8, 0.875. And yeah, we could do it by hand. We did some of those by hand. The book's got the longhand division there, right? You tack on all these extra zeros after the decimal and you pull them all down until you either get a remainder of 0 or sometimes you don't get a remainder of 0, right? 1/3, you're never going to get a remainder of 0. You're going to sit there and get 3's forever. It's what they call a repeating decimal. Okay, so we usually write that as 0.3 with a bar on top. That indicates the 3 repeats. Okay, or you just round it off somewhere. You see the squiggly equal sign just means, hey, it's been rounded off. So maybe you call it 0.33. Or the 4/11. That's another one, but that one repeats in a pattern. You see it's 0.363636. It keeps going in that pattern. Okay, so we would write that as 0.36 with a bar on top of both the 3 and the 6. Okay, or you'd round it off somewhere. Okay, but fraction to decimal is just perform the division, either longhand or with your calculator. No big deal there. Okay. Mixed number as a decimal, well, the whole number part's going to stay. If I had 2 and 5/6 as a decimal, well, the 2 is still going to be there. I just got to figure out what is 5/6. The 2 is the 2, so what do we got here? 5, 6, 80.83 repeating, so 2.83 repeating. Okay, so the 2 just comes along because it's the whole number. Example 14 at the bottom says let's take 3 2/5. Okay, well, the 3 is still going to be there. We just need to take 2 over 5.4, 3.4. Okay. Comparing fractions, mixed numbers, and decimals, which one's bigger, which one's smaller. Well, you got to get something common, either a common denominator or turn them all to decimals. You got to have something, some way to look at them, so you know what's what. Common denominator, if you're looking at 3 fractions, that's probably a good way to go. If you look at example 15, and we're going to do this when we start adding fractions. If I have these 3 fractions, and I want to reslice the pie so they all have the same number of pieces, okay? I have to figure out what that number is, because what's going to be a number that I can turn a 12 into, a 15 into, and an 8 into. What's this bigger number out there that I can say 12 times something is that number, 15 times something is that same number, and 8 times something is that same number? What's that big number out there that's going to do it? Well, we did this already tonight when we were finding the least common multiples, the LCMs, okay? We took those numbers, remember, and we started counting, 12, 24, 36, and then we said 15, 30, 45, and then we said 8, 16, 24, and we kept going. This was like the hard way, and eventually we found a match, right? And then we said, yeah, there's a better way. You find all your primes and blah, blah, blah. We had that procedure. Well, that was just to find the least common multiple of 3 numbers. But if it's a fraction, we change terminology a little bit. We want to find the least common denominator. Okay, so we're only interested in the 3 denominators. I want my 3 denominators to match, but it's the exact same procedure. I'm going to find the lowest common multiple of the denominators. I'm just going to call it the least common denominator. Okay, so we want to find these 3 fractions, and this will be a requirement, next week when we start adding these fractions. You have to have a common denominator. So let's just practice how to find it. We could count like this, but this one looks like it might be a big number. We'd have to do a lot of counting to find a match. So if you remember more the procedure way we did it, we factor down the primes. So 4 times 3 and 2 times 2. So the 12 factored into 3 times 2 squared. And the 15 is 5 times 3. All right, so the 15 is 5 times 3. And the 8 is 4 times 2, but then the 4 is again 2 times 2. So 8 is 2 cubed. When we were finding this least common multiple, or now we're going to call it the lowest common denominator, everybody gets to come out and play. So the 5, the 3, and the 2. Okay, so the lowest common denominator is going to have 5 times 3 times 2 at least. But then when we had these ones with the exponents, we wanted to pick the largest exponent. So it'll be 2 cubed. So 5 times 3 times 2 cubed is going to give me my answer. In this case, it would be 120. Okay, so if I kept counting by 12s, eventually I would hit 120 here. If I kept counting by 15s, I'd hit 120. If I kept counting by 8s, I'd hit 120 eventually. That's my lowest match. There's other matches, but that's the lowest. And we always want to find the lowest when we're messing around with these fractions. Okay, so that's how we would do that. Okay, let's use this idea now to compare fractions. There's multiple ways to compare fractions. When we start adding, well, like I said, next week when we're adding fractions, that's going to be the requirement. Find the lowest common denominator and then turn every fraction into the equivalent fraction with that lowest common denominator and then add or subtract them. So That's fun for next week, but we can also use this same idea to compare two fractions. If I ask you which is bigger, 1/4 or 5/16? Maybe you think 5/16 is bigger just because it's got bigger numbers, but that's not necessarily the case. How can we tell for sure? Well, one way is the decimal comparison. Okay, so that's not what the book's telling us to do right now, but that is a way. 1 divided by 4 is 0.25. Okay, 5 divided by 16 is 0.3125. So this is going to be bigger because it's a bigger decimal. But right now we're doing an exercise with denominators and fractions. So I want to think of it that way. I need to find the lowest common denominator of these two numbers, a 4 and a 16. Now, I hope we're going to get to the point where we can just kind of spot it, But if we don't know, we do that procedure. We factor the 4. 2 times 2 is 4. Okay, and we say, okay, 4 can be thought of as 2 squared. We factor the 16 all the way down to primes, right? 4 times 4 is 16. 2 times 2 is 4. 2 times 2 is 4. So that's really 2 to the power of 4. The least common denominator, which was what we called the LCM earlier tonight. Same exact thing, just a different purpose. Now we're only looking at denominators. Before we were just looking at random numbers. The least common denominator says everybody gets to come out and play, but we only have 2's. Okay, so 2 is everybody. And we pick the highest exponent, so 2 to the power of 4. So my least common denominator in this case is 16. So what that is saying is, hey, I can take you 1/4 and I can turn you into denominator 16. Okay, we just determined we can do that. All right, well, let's do that. So I can multiply by 4, multiply by 4. So that's going to be 4/16. So the comparison was 1/4 versus 5/16. And we said, aha, at 1/4, I'm just going to think of you as 4/16. So now it's 4/16 versus 5/16. Who's bigger? Now it's obvious who's bigger. This one's bigger. Okay, here, not quite so obvious, right? But now it's unmistakable. When you have the same denominator, it's like having a 16-piece pie, and this one's only got 4 pieces shaded, and this one's got 5 pieces shaded. Who's bigger? Obviously, the 5 is bigger. But you can't conclude that until you have the same denominator. Now you can conclude that. Okay. One other way to do that is with that cross multiplying. Remember we said when you have equivalent fractions, 4/16 equaled, we said 1/4, right? These two things are equal now. We said that when you have this equivalent fractions, you can do this thing we call cross multiply. And you can see one way is going to get me 4 times 4, and the other way is going to get me 16 times 1. And if they're the same, then I know these two things are equal, right? Well, here we know they're not equal, but we're being asked which one's larger and which one's smaller. If you look down here at this shaded yellow box here, that same problem. Which one's bigger, the 1/4 or the 5/16? We could also use cross multiplying to help us with that answer. You just got to be careful which way you go here. You got to always keep the numerator on the same side it was on. So, in other words, when you cross multiply, you have to keep the 1 here times the 16, and you have to keep the 5 here times the 4. It would be easy to kind of maybe get confused and say, oh, well, can't I do 4 times 5 over here and 1 times 16 over here? No, you have to keep it. When they're equivalent fractions, it doesn't matter because it's going to be equal on each side. But when they're not equivalent, we have to pay attention to the order because we need to keep the numerators on the proper side. So now we're saying this one's 16, this one's 20. Well, obviously 20 is bigger than 16. And if 20 is bigger than 16, then that means that 5/16 is bigger than 1/4. So we can use this cross multiplication procedure to let us evaluate the fractions also. Okay. I like finding the common denominator better just because we're going to have to do that anyway. All right, let's quickly look at a couple more things here. Example 17, is it possible to have a pipe with an outside diameter of 5/8 and an inside diameter of 21/32. Is it possible, or does it make no sense whatsoever? Can this dimension be 5/8? Oops, and I just wrote the slanted slash, because that's what I do in my other life. I deal with pipe sizes and I write it like that, 5/8, but work with me. Sorry about that. In math, I want to be real good about fractions having a top and a bottom, not a slanty slash. And the inside is 21/32. I'm just going to write it here so we can see it. Does this even make sense? Obviously, the inside diameter must be smaller than the outside diameter, or this whole thing doesn't make any sense. So in other words, if I take 5/8 and I want to turn it into something over 32, how would I do that? Well, 8 times 4 is 32. 5 times 4 is 20. So 5/8 is equivalent to 20 over 32. So in my picture here, we're making the claim that this outside of the pipe is 20 over 32. But this little inside is 21 over 32. That can't happen, right? It's impossible. The inner diameter cannot be smaller than the outer, cannot be larger than the outer diameter. And that's exactly what this is. So no, can't do it. Okay. So the numbers can be very full, deceiving. 21 and 32, we got big on the brain because those are big numbers. Well, 21 over 32 is smaller than 5/8. 5/8 is bigger. No, I said that backwards. I said that backwards. It is bigger, okay, but just because we had bigger on the brain doesn't mean anything, okay? We have to compare the two like this, okay? But 21/32 is larger than 5/8. So this problem is can't happen. All right, one more, 2 more. Example 18 says, two drill bits have diameters of 3/8 inch and 5/16 inch. Which one makes a larger hole? All right, so 3/8 versus 5/16. I need a common denominator to compare them. Now we can tell that I can turn an 8 into a 16, right? I mean, we know I can turn an 8 into a 16. So 16 is going to be my lowest common denominator. And we'll do more of this next week, finding those common denominators. But all I have to do to compare is I need to take that 3/8 and I need to turn it into denominator 16. So I asked myself how to do that. Well, times 2 times 2. So 6/16. So when I'm being asked to compare 3/8 versus 5/16, I'm really being asked to compare 6/16 versus 5/16. And now it's real obvious who's bigger. Okay, 6/16 is bigger, which means 3/8 is bigger. Okay. All right. Last one. The specifications of an electronic tablet state that the length is 15.8 inches and the width is 10 inches. A carrying case is 5 7/8 inch by 10 1/8 inch. Will it fit inside? Okay. Here's one where decimals probably make a little more sense than fractions. It's always good to have a picture. I've got this case and I want to put my tablet inside the case, right? I want to see if it fits. The specifications of an electronic tablet say the length is 15.8 inches and the width is 10 inches. So I'm writing the dimensions on and I just did the hash mark for inches. That's my other life, sorry. I'll write it over here, cross that out, 10 inches. That's my tablet. How big is my case? The carrying case is 15 7/8 inches and 10 1/8 inches. Okay, will it fit? Does this make any sense? Okay, here's a case where I think going to decimals would be the easiest route. Now, in the case of the 10 versus the 10 1/8, I mean, it's obvious immediately, right? 10 1/8 has got to be bigger than 10. So even if we don't take the time to take that 1/8 and turn it into a decimal, I think we know that's going to be good, 0.125. So this is really 10.125 inches, the case. And the tablet itself is only 10, so it's going to fit that dimension. What about this other dimension, 15 and 7/8. Well, what is 7/8? 7 divided by 8 is 0.875. So 15.875. The case is 15.875. The tablet's only 15.8, so it should fit inside there, right? So I would say, yes, it's going to fit. Okay. All right. What do you think about that?
It's quite a bit.
Pretty good.
Okay, it is. I mean, this was an introduction to a lot of things we're gonna use now next week when we actually start adding, subtracting, multiplying and dividing fractions and mixed numbers. We're gonna use these common denominator stuff and reducing, so. So our first homework was, in the homework number 2, you can get it on, just do the stuff that makes sense, once you get to something you haven't seen yet, that's a good stopping point. And we'll go from there next week. Anybody have any questions?
Yeah, I wanted to ask you about the exam. Well, how many questions will be on the exam?
Oh, boy, I don't remember. How many should there be?
10?
One.
I don't remember. I have to double check.
Write an essay,
Yeah, I don't remember. I'm sorry, but a reasonable number for the time. If you're worried about the time, I'm not making it crazy or anything. It's I mean, we're gonna have the whole night to get it done, and it's really not designed to take the whole night, so I think there'll be plenty of time. But I can look at I don't have it at the top of my head. I'm sorry. How many questions? The practice exam will start popping up here in I think next week. 2 weeks in advance of the real exam, a practice exam goes live in MATLAB, and then you can get in there, and the practice exam is very, very, very similar to the real one. So you can get in there and see exactly what to expect.
Okay.
Okay.
When is homework number 2 due by?
I believe 2 weeks from now. Yeah, let me double check that. I believe it's 2 weeks, right? Let's see here. What is it? February already? Yes, it is. Homework number 2 is due on the 19th.
Thank you.
Okay. Then there'll be a homework number 3 due 1 week after that, and that's also going to be our exam night at February 26th, I believe, is also our exam night. So yeah. Okay.
All
Anybody,
right.
anything else? Okay, have a wonderful week. Stay warm and have fun Sunday night if you're doing anything fun. And I'll see you next week.
All right. Good night.
Okay, thank
Have
you.
a good night.
Have a great time, Mr.
You
Cooper.
Thank you.
Good night.
Thanks. Have a good night.
Thank you.